We're now going to jump into the reactions of preparing carboxylic acids, and we're going to start off with reactions that we are already familiar with. So, for example, we can oxidize primary alcohols and aldehydes into carboxylic acids using chromic acid, as shown here. So, primary alcohol in the first example using chromic acid, which can come from either using chromium trioxide as shown in this example, or sodium dichromate, which is a reagent we have used in the past with sulfuric acid and water to make chromic acid as well. That primary alcohol will be oxidized to a carboxylic acid. Note that this reaction goes through an aldehyde, which then gets oxidized to a carboxylic acid. If we start off with an aldehyde, we can do the same reaction to make a carboxylic acid. Another method used to make carboxylic acids is the oxidation of the side chain of aromatic compounds. This can usually be done with strong oxidizing agents such as chromic acid or potassium permanganate. Here is an example. This benzene with an ethyl side group can be oxidized with chromic acid, whether we use chromium trioxide or sodium dichromate. We will mix it with sulfuric acid and water and heat it, usually around 100 degrees or more. That ethyl group will be turned into a carboxylic acid. Here's another example containing a methyl group, a propyl group, and a terbutyl group. Note that in this example, only the methyl group and the propyl group are converted into carboxylic acids. The terbutyl group is not. What we learn from examples like these is that in order to do an oxidation of the side alkyl group of an aromatic ring is that a benzylic hydrogen is required. In other words, here's the benzylic carbon. We must have a hydrogen, at least one hydrogen at that position. So if we have an ethyl group, that can be converted into a carboxylic acid. If we have a methyl group or a propyl group. In the case of a terbutyl group, that carbon only has bonds to other carbons. It does not have a hydrogen, and therefore it cannot be oxidized. It is believed that under this oxidation, a benzylic hydrogen, is abstracted and converted into a radical, which starts the reaction. Note that no matter what the size of the chain is, it will always be converted into a carboxylic acid. So we can have a very long alkyl group, and it will still be converted into a carboxylic acid. Potassium permanganate is a strong oxidizing agent that if we heat an alkyl group on a benzene compound to around 100 degrees Celsius, we can oxidize that side group into a carboxylic acid. So for example, a methyl group can be oxidized into a carboxylic acid. Similar to the oxidation with chromic acid of the side groups of aromatic compounds, we must have a benzylic hydrogen on that carbon next to the benzene ring. Otherwise, the oxidation does not occur. So to make carboxylic acids is by using a Grignard or organolithium reagent with dry ice. Here's a couple of examples. If we have an alkyl halide and we add magnesium or lithium, we can make the Grignard reagent or an organolithium reagent. And then if we add CO2 or dry ice, which is the solid form of CO2, we can then make a carboxylic acid out of that Grignard or organolithium. Note that the product from this reaction will have the same number of carbons as the Grignard or organolithium reagent, plus one more that comes from the CO2 molecule. So in this example, we have 4 carbons in the Grignard reagent, 4 carbons in the organolithium reagent. If we get one more from CO2, we will have a carboxylic acid that has 5 total carbons. The next example is a phenyl Grignard reagent that is mixed with CO2 followed by aqueous acid to make benzoic acid. Here's a look at that mechanism. So a Grignard reagent will add to the carbon of CO2. So think of this as a carbanion adding to the slightly positively charged carbon of CO2, similar to the reaction of Grignard reagents with a carbonyl of a ketone or an aldehyde. That will lead to breaking one of these double bonds to create the carboxylate ion that you see here. And then lastly, if we add aqueous acid, we can protonate that oxygen to make benzoic acid. Here's one more example with an alkyl halide. If we add magnesium or lithium, we can make a Grignard or an organolithium from it. Then if we add CO2, we can add a carboxylic acid. And note that we had to add aqueous acid at the end to turn the carboxylate ion into a carboxylic acid. Notice the product will have an extra carbon from the CO2. So we originally started with a cyclopentane. We're going to add the carboxylic acid on the outside. And we're adding essentially one more carbon because of the CO2. In this reaction, we're going to give the missing reagents from the following reaction. We're starting off with an alkyl halide, and we're converting it into a carboxylic acid. Notice that the carboxylic acid has an extra carbon compared to the original alkyl halide. This reaction is set up to be a carboxylation of an organolithium or a Grignard reagent. So if we start off with an alkyl halide, if we add magnesium or lithium, we could convert it into a Grignard or an organolithium. And then if we add CO2, we can add a carboxylic acid where that chlorine is. And so the reagents that are missing are magnesium or lithium, followed by CO2, followed by aqueous acid. One of the reasons why nitriles are in the same chapter as carboxylic acids is because nitriles are very easily converted into carboxylic acids by hydrolysis. If we heat a nitrile with acid or base, we can turn them into carboxylic acids pretty easily. Here's an example of a base catalyzed hydrolysis of a nitrile. So if we start off with a nitrile and we add sodium hydroxide, water, and heat, and then in a second step, we add aqueous acid, we convert it into a carboxylic acid, plus ammonia as a byproduct. The reaction starts by the sodium hydroxide, the hydroxide in particular, which is a strong base or a strong nucleophile, adding to the carbon of the nitrile, breaking one of the pi bonds to create this intermediate. That nitrogen has a negative charge, which will then be protonated by water, creating this intermediate. The intermediate will tautomerize into an amide. So notice the double bond is between the carbon and nitrogen, and there's a single bond to an oxygen. And then in the product of this tautomerization, we exchange the double bond, and now it is now between the carbon and oxygen, and there's a single bond to the nitrogen. As a reminder, tautomerizations are the rapid interconversion of constitutional isomers. So the two compounds you see here at the bottom of the slide are tautomers of each other. The next step, or the second half of this reaction, is essentially the hydrolysis of an amide. We're going to see this again in more detail in the next chapter, chapter 21. But here is how the reaction occurs. Sodium hydroxide, the OH in particular, will attack the carbon of the carbonyl. break the double bond to create a tetrahedral intermediate. And then that tetrahedral intermediate will break down to eliminate the amino group. So the oxygen will reform the carbonyl, eliminate the NH2. The product from that will initially be a carboxylic acid as shown here, but because this reaction is done under basic conditions, so sodium hydroxide is present in the reaction, it will deprotonate this acidic hydrogen of the carboxylic acid. For that reason, we have to use aqueous acid in a second step to neutralize that sodium hydroxide and convert the carboxylate ion into carboxylic acid. So any reaction that leads to making a carboxylic acid that is done under basic conditions, we always have to use a second step where we add acid to convert it into a carboxylic acid. Here's a look at how we can convert an alkyl halide into a carboxylic acid in a two-step sequence. I'm going to use the example of the synthesis of ibuprofen to illustrate this point. So if we start off with an alkyl halide, usually we need to use a primary or a secondary alkyl halide. If we add a cyano group, which is a good nucleophile, we can do an SN2 reaction and convert it into this nitrile here. Then if we hydrolyze the nitrile under basic conditions, we can convert it into a carboxylic acid. So we can go from an alkyl halide to a carboxylic acid through a sequence like this by first adding a cyano group and then hydrolyzing that cyano group. Nitriles can also be hydrolyzed under acidic conditions. So for example, acetonitrile, when mixed with sulfuric acid, water, and heated, will be converted into acetic acid plus ammonia. The reaction starts by protonating the nitrile nitrogen with sulfuric acid. We could also use the hydronium ion in this step. Then water, which is a poor nucleophile, will add to the carbon of the nitrile. That leads us to this intermediate. The water has now a positive charge, and so we'll use a base like the conjugate base of sulfuric acid. We could also use a water molecule to remove a proton from the water that just added and also get rid of the positive charge on the oxygen. That leads us to this intermediate, which tautomerizes to an amide, as we saw in the base catalyzed hydrolysis of nitriles. The second half of this mechanism is a hydrolysis of an amide under acidic conditions. We'll look at this again in a later chapter, but for now, we'll take a quick look at how this reaction occurs. It starts off with the amide oxygen on the carbonyl being protonated by sulfuric acid. Again, this can be done with the hydronium ion. That leads us to this intermediate, which gets attacked by water. The carbonyl is broken. We get now to a tetrahedral intermediate. A water molecule or the conjugate base of sulfuric acid can remove this proton, form a carbonyl here by eliminating the amino group. That leads us to a protonated carboxylic acid, which then loses a proton by using the conjugate base of sulfuric acid or another water molecule. And if we remove that proton, we will have now the carboxylic acid. In this question, we want to prepare phenylacetic acid, whose structure is shown here, from benzobromide. There are two methods we can use to go from benzobromide to phenylacetic acid. In both cases, we have to use a combination of reactions that we learned about. For example, we can add sodium cyanide to benzobromide to do an SN2 reaction and obtain this nitrile that you see here. Then we can hydrolyze that nitrile either under acidic conditions as shown here. By the way, we would need to heat this reaction. We can also do it under basic conditions, so sodium hydroxide, water, and heat will do the same thing. And we could obtain from that phenylacetic acid. A second strategy we can use to go from benzoyl bromide to phenylacetic acid is by using a Grignard reagent or an organolithium reagent. So if we add magnesium or lithium, we can get this benzoyl Grignard reagent, or we can make a similar organolithium reagent if we use lithium as our metal. That carbanion can then add to CO2 followed by aqueous acid to make phenylacetic acid.